And all right, so ANOVA, and I've heard people say ANOVA, ANOVA. I never know what's the right way, but basically it stands for analysis. Let's see if I can highlight this. Analysis of variance. Go figure, right? But I actually think understanding that that's what that actually represents, it actually makes a lot of sense of what's going on here. And basically, it's a way to look at all the variance of different groups all together and say, all right, look at all these groups together. Is there actually something to be found in here? Or is it just like, because we're looking at 5 different groups, that it just happens to be like one of the groups looks significantly bigger for us? So that's the idea of basically analysis of variance. We're looking at the variance of the different groups with the variance of the overall group. So you can kind of imagine it like back to the XKCD with the acne and jelly beans. You guys remember that little comic, right? So you can kind of think of it like analysis of variance is like you basically say, well, what's the variance for each colored jelly bean and like how much acne it produces, right, for a person. And then the variance of the overall group is if you've ignored all color, right, of the jelly beans. And so that's the idea of ANOVA, is basically you're trying to determine if there's an actual variance that's different from the group from the rest of them all together. All right, so I'm gonna try my best here to try to like put this together, because I'm also trying to avoid some math, like really for us to like dive deep into it, because I don't think we need to go into that direction. And honestly, the cases where you can go find this online, like about like what's the mathematical derivation and all this stuff, and I don't know, I think it doesn't really help in the end. I think it just ends up being a little more confusing, but we're gonna see how well it goes. So the first thing you basically say is say, how much do groups vary? So basically you take what they call the sum of squares between in the group itself. So the residual, excuse me, we're gonna call this SSS underscore model. So SSS, sorry, I can never do this right, SS model, residuals from the mean, all the groups together. So basically this is saying, okay, like how much does it differ, you know, from the groups, like, or for the whole overall group together. And then we have how much it varies from within for each group. And we'll call this SS residual, right? So each group's residual summed. So what this really looks like between these two things, like, okay, these are some acronyms, some letters, doesn't matter. What we basically do, and I'm gonna draw here, and we'll see how well I draw. I should just get a pen so I can like draw for you guys, but drawing with mouse is good enough. Okay, so pretend we have like, let's say blue jelly beans, right? And let's say this value is like sugar content or something like that. Something easy to like measure. So this is like amount of sugar, and then right here, we can say, okay, well, these are the different jelly beans. So we measure one right here, one right here, one right here, one right here, maybe another one right here. So we had like 5 different jelly beans with different sugar content, right? Then we have maybe something like a red jelly bean, right? And we have something like the sugar content here, sugar content here, sugar content here. This is like really low. And then maybe something like, I don't know, like this. Okay. Oh, let's do one more. Let's do another one down here. So like pretty low, okay? And so we have these 2 jelly beans. And let's just, for the heck of it, let's add the third one. Purple? Purple sound like a good color? I changed it. I'm gonna do orange. So, all right, orange. Are they even orange jelly beans? I don't know, maybe. Okay, I see some nods. Okay, it's almost Easter, I guess. So, I don't know, jelly beans are in season. All right, so what you would do for each of these jelly beans here, you might say, okay, what's the average sugar content? So like the average sugar content for this guy's like, oh, let's say it's about like right here, right? That seems about right. For the red jelly beans, maybe the average is closer to like over here because it's a little bit higher up here. And then let's say blue, I'm just gonna making something up about right here. That seems more or less. I made up this data. It's not like it needs to be perfect. And so the big thing is that you want to say, hey, is there a difference in jelly bean or sugar content for the different colored jelly beans, right? So the idea here is that you say, okay, well, let's just go ahead, ignore all the colors. What's the average, you know, sugar content for all these jelly beans all together? And the average for this is like, I'm just going to draw a little black line. Let me make it a little better. I'm going to say the average is probably right about like here. Seem about right? It should split them about in half, right? So it's not perfect, but let's just pretend that's the black. It's like all the jelly beans ignoring color. This is the average right here. And basically you want to say, hey, are these averages for each colored jelly bean, are these averages significantly different than all of them put together. Basically what this is saying is like, hey, if I want to know how much sugar is inside a jelly bean, does it help me knowing the color of the jelly bean? Or should I just ignore the color and just say, oh, that's the average? So like, for example, if you were trying to say, oh, there is a significant difference between blue, red, and orange or some case, you would say, hey, tell me what color the jelly bean is. I'll tell you the average of those jelly beans, and that will give you a better estimate than just saying the overall sugar content. Does that make sense? Okay, everyone's following me so far? Okay, I don't think anything too crazy happens yet. So now what we say is like, okay, well, we want to find the variance of like from, let's say, all the jelly beans from this average right here. And this average, we call this the model. And why we say it's a model, we're basically saying this explains, this is modeling the jelly bean sugar content. We don't actually know what the sugar content of the jelly bean is, but we can say, well, we can predict that the sugar content is the model itself. And when we do this like for values like this, and we'll see this in linear regression, we basically just take the average. And the average is like, oh, whatever the average is, that is your model. That is kind of your baseline. Make sense? And then we're saying, hey, if we know extra information, can we do better than that original model? So what we can say is like, well, okay, what's the variance of this model? Does anyone remember what's the formula for variance? So sigma squared. And I know it's tough to say exactly.
Like x bar squared minus x squared over something. The n and n.
Yeah, something like n.
Yeah.
Something that looks like that, right? Like
yeah.
Like that. You're close. Not quite. What you're looking for is you got the x squared. It's actually all of this squared.
Oh right, yeah.
So it's the differences squared from like this is like the population average versus like the actual single point divided by n. But we actually
n minus 1, isn't it?
That's for sample, not population.
Yeah, it's if you're taking a sample of a sample. So we don't worry about degrees of freedom here. But in general, like we're getting like a ballpark, right? It's like, oh, we just divided by n. But in this case, it is actually just n. But also we have to sum this over each value of n. So properly I should put like an I here. And this means that capital sigma, which looks like an E right now, is supposed to be summing over all the differences of each what's it called? Each point squared. Does that make sense?
Mm-hmm.
So for those people who might not be as fluent in Mathanese, what that looks like is like x1 minus x bar all over squared plus x2, so the second point, minus x bar all over squared. And then we just do that for every single data point, right? And then divide the whole thing by n. Does that make sense? I know it's a little messy here, but everyone follow me on that? Okay, so what we'll actually call this sometimes is we'll call this the sum of squares. So you can kind of see like, oh, that kind of makes sense, right? It's the sum, right? This is the sum right here of the square differences, right? In fact, we can actually, like we can talk about this in linear regression, we actually literally draw squares and sum up the areas of those squares. But you can things like, oh, that's called the sum of squares. Why do we call it SS, right? So the sum of squares. And then we can do two parts. We can say, okay, let's look at the overall model. So SSS, I call it model here. People will call it different things depending on what you look it up, but the idea here is that we're looking at the overall part. We basically say how far are each of these data points from this black line. So X bar is this black line, and then XI is the actual point where it is in the Y-axis, okay? So we have that guy. Then what we do for every single group, we calculate how far that individual point is from its quote unquote little model, like this little blue line, this little red line, this little orange line. So all the blue ones will have a certain variance, SS, right, the sum of squares, from this model right here, which is basically just considering just the blue ones. And then the red ones will have a different sum of squares for this one right here. So that's kind of the idea, is like these are the kind of residuals of like what's left over in here. And then what we can do with that information, does everyone follow me? Like you would calculate the variance for this guy, variance this one, cool. All right, then what you would do with this guy, you basically would calculate something called an F statistic, which is sometimes also called like an F ratio and stuff like this. It's basically based off of something called the F distribution. Yeah, statisticians are even like more like boring and naming stuff, but that's probably good because it makes it nice and easy. So this F statistic, right, basically, and I want to let you guys know, this is not the actual equation for find the S statistic because there's one thing we didn't consider, okay? Does anyone got to guess what we didn't consider, at least for the residuals when we were drawing out those jelly beans? So what if you only had like 4 red jelly beans and then like 50 blue jelly beans? Like you can probably guess like, oh, there might be some, there's some difference in there. So we have to consider degrees of freedom, right? Basically saying, well, if we have more jelly beans and it's clustered around this, mean for that colored jelly bean, oh, we should consider that. So you also have to basically consider the degrees of freedom here. So that's kind of correct, almost like a sense like a correction factor, right? Of saying, oh, how much are we actually considering? What's interesting with like the SS model and stuff like this and this residual, we actually have to consider, what's it called? Like how many different colored jelly beans we have. So degrees of freedom then is not dependent on how necessarily just how many jelly beans for each color we have. We say how many colors do we actually consider. So just know that basically that one of these are going to consider, well, how many jelly beans do you have in that particular group? And then how many jelly beans, different colors do you have, different categories you have considered. And those will be 2 different degrees of freedoms that will correct it. Now, the nice thing about this, I'm telling you all this is because, and I'm not showing you the equation, is because in reality, you're never going to have to write this yourself. You're going to use a computer to do this for you because like it's a lot easier to just basically, here's all the data, here's the categories, and the computer can basically calculate for you for your function. So in general, you basically would just get like an F statistic and say, hey, and this, the computer program, whatever you have, right, package, is just going to pop out saying, oh, here's the F statistic. Okay. Does this make sense to everyone? Okay, but the main idea here is we're basically trying to figure out the ratio of variances. How much does the jelly beans vary from that overall model? That's kind of like the null hypothesis right there, right? It's kind of like, oh, there's no difference between colors. And then what if there is a difference between colors? You look at the variance between each of those groups. Cool. All right, cool. So everyone's following me on that? Any questions on like just overall like logic of that? No, pretty good. Okay, and we'll see how we actually code this because it's actually a lot easier than it sounds.
I have a question.
Oh yeah, go ahead.
I don't, for some reason, when I Google this, like, they just don't recognize my question. But like the FS and covariance kind of like in my head seem to be doing like a similar thing. Like just with like comparing the variances, right?
You said covariance versus F statistic?
Yeah, I know, I understand that they have nothing to do with each other, but I just don't see it.
Yeah, so the F statistic is a specific ratio essentially that we're designing that compares it to what we call the model of, which is the average of the overall group, and then of all the groups individually. So the covariance is much more in the sense of comparing different variables between each other. So it's a little bit different. Well, I should say it is different, but you'll probably see something similar. If you guys remember what covariance looks like, I'm just gonna quickly write this in case you guys, oops. It looks something like X minus X bar times Y minus Y bar, right? And then X and Y are 2 different variables and stuff, and saying how do these relate together? I would say in some ways this is closer to like when you talk about like correlation with 2 different variables versus like looking at one group and stuff like this. So you could maybe argue it, but it's definitely calculated in a very different way than the F statistic.
I got you. Thanks.
No problem. All right, cool. So once we have that, it's like, okay, what do we assume? So there's always assumptions. And these are actually really important because we'll see this again in linear regression. So basically, one, as always, we assume the samples are independent from each other. So there's not a dependence on like how we collect this information from one group to the other. Each sample is normally from a normally distributed population. So that's pretty typical stuff. These 2 in general are the ones where just like, to be frank, it's like, we'll do like a lot of these things like, oh, you're supposed to have the assumptions, and we go, it's close enough. Like we can probably do this and move on. The one that's going to be the biggest one, which we'll see, is basically the population standard deviations of the groups are all equal. And this is properties known as, I can never pronounce this word, homeoscedasticity, which we'll see this word again in linear regression. Yeah, I know, right? Like this is a ridiculous word. But in general, what we'll see basically is we can test for homeoscedasticity. And this is the thing that when you're trying to do linear regression, hence also ANOVA, because they're basically the same thing, this is the one that's going to screw over your model, essentially. It's going to be like, oh, like this assumption fails, and now basically whatever you have for linear regression, it's not going to work. A very, very quick thing, we'll go into more detail in the future about what this is, but basically you can kind of think of your linear model in ANOVA. Basically, if you have like a line right here, but your data looks something like this, like expands out like this, like I'm just imagining like the data points are all around here. And that blue is kind of like trying to do the best to describe it. This line is not really doing a great job of describing the data. What's happening here is basically the variance is changing as we increase in value on the x-axis. That's essentially what homeoscedasticity is. That the variance will change over some other metric that's not defined in here. So this is the part that we have to worry about the most. But for the most part, these other two, we're usually pretty good, even if they're not 100% true. Okay. So I thought I'd just point this out. Know that technically if these assumptions fail, there are other tests, for example, the KWH tests, right? Really fun. I'm not even gonna try to pronounce these things. These are named after people. I'm sorry, people who did amazing things that I can't pronounce names for. But just know that there's also less power to actually do this. So you have more chances of essentially getting false negatives, which is not the best, right? So in general, you probably won't ever use this. I mean, I shouldn't say you won't ever use this, but you likely won't use this as a data scientist because there's other things we can do than just doing different hypothesis tests all the time. Okay, cool. All right, sounding all good? Good to move on a little bit?